the night sky hums with silence. Among the stars, a traveler from beyond drifts inward, unbound by the sun, on a path never seen before. This visitor is called 3I Atlas, an interstellar comet passing through our solar system on a one-way journey. The comet's path is a quiet promise and a firm fact. It arrived from the dark between the stars on a trajectory that is not bound to our sun. That path is hyperbolic, which means this visitor will pass through once and then continue outward into interstellar space, never to return. Its motion was measured precisely, and from those measurements astronomers know where it will go and how close it will come to the worlds of our solar system. Because the orbit is well understood, the question of danger is answered with certainty rather than fear. The comet will not cross Earth's orbit closely. Its closest approach to Earth is about 1.8 astronomical units, roughly 270 million kilometers, which places it comfortably on the other side of the Sun when nearest to us. In simple terms, this comet will pass by our planet at a distance larger than the distance between Earth and the Sun, so the probability of any collision with Earth is effectively zero. Planetary defense teams and astronomers alike agree, there is no impact risk from this object. A quieter close encounter will happen with Mars. The comet will pass Mars at about 0.19 astronomical units, roughly 29 million kilometers, giving spacecraft orbiting Mars a rare front-row seat to an interstellar visitor. That close approach has prompted a flurry of planned observations from orbiters and rovers, instruments tuned to catch the light filtered through the comet's coma and the dust streaming from its heart. Those instruments will watch the chemistry and the dust, and they may reveal textures and behaviors no telescope on Earth can see so well. The comet's closest approach to the Sun, perihelion, will occur near the end of October 2025 at about 1.36 astronomical units, just inside the orbit of Mars. At that time the comet will be warmed more by the Sun's light, and its activity, sublimation of ices, release of gas and dust, may change in strength and character. Comets often brighten and evolve as they feel the Sun's heat, and astronomers expect changes in the coma and tail as the object moves through perihelion. Estimates of the nucleus size vary, and that uncertainty colors some of the expectations for how much dust and gas the comet will release. Size estimates derived from Hubble, ground telescopes, and thermal models place the nucleus anywhere from a few hundred meters up to several kilometers across. If the nucleus is on the larger end of estimates, its mass and internal structure will affect whether it remains intact or sheds larger fragments as it warms. Observers have not yet seen catastrophic fragmentation. The comet so far has behaved as a typical active comet, albeit with some unusual chemistry. Chemistry is where surprises have already arrived. Spectroscopic data from space telescopes and ground observatories reveal that carbon dioxide is unusually abundant in the coma, with a CO2 to H2O ratio far higher than what we usually see in solar system comets. That signature suggests the comet formed in a different chemical environment, or that its journey through interstellar space exposed or preserved ices we rarely encounter locally. If CO2 dominates, the way the comet sheds material and how its coma evolves with distance from the Sun will differ from the familiar behavior of many comets we have studied before. Polarimetry and color measurements add texture to the portrait. The light scattered from the comet's dust is more polarized than is typical, and the spectrum is redder than many native comets. Those clues hint that the dust grains may have different sizes, shapes, or composition. Polarization and color are subtle signals, but they are powerful. They tell astronomers about surface texture and grain properties the way a fingertip tells a blind person about the grain of wood. Combined with chemical measurements, they suggest that this interstellar voyager carries material unlike the familiar comets formed in our protoplanetary disk. Observers also look for non-gravitational acceleration, small pushes from asymmetric outgassing that can change a comet's path slightly. For 3I Atlas, early analyses show little to no measurable non-gravitational acceleration so far, implying either relatively symmetric outgassing across the nucleus or a dense nucleus that resists being nudged. That detail matters because a strong non-gravitational effect could complicate precise long-term orbit predictions. For now, the orbit remains well constrained and the predicted distances to planets remain firm. What scientists have discovered so far is a balance of the familiar and the strange. Familiar because this object behaves like a comet in showing a coma and tail and in producing water as well as other volatiles. Strange because the composition and dust properties are different enough to make astronomers pay close attention. The expected observational show will be quiet and scientific, a sequence of spectra, images, light curves, polarimetry, and spacecraft snapshots that together will teach us about how this small world formed and what interstellar comets are like. Instruments from Hubble to JWST to orbiters at Mars will gather the light and whisper back their measurements. For a person watching from Earth with a small telescope or binoculars, the show will be subtle. 3I Atlas is not predicted to become a naked eye object. Its peak brightness will likely remain faint compared with the brightest comets observers remember. For astronomers with large telescopes and space observatories, the spectacle will be rich in data rather than dramatic in brightness. For science and for the slow comfort of knowing more about the cosmos, the visit will be a gift. In short, the probability that 3I Atlas will approach Earth in any dangerous way is effectively zero. It will pass safely at great distance. It will come closer to Mars and to the Sun, offering a chance to study an interstellar piece of ice and dust up close in ways we rarely can. It will teach us about chemical diversity, about dust and ice physics, and about the kinds of small worlds that wander between the stars. Astronomers will watch, and we will listen to what the light tells them, what scientists have discovered so far. The story of this comet unfolds slowly, like a quiet book of cosmic history. Each observation is a page, each spectrum a sentence, each faint flicker of light another whisper from a world that has traveled for millions, maybe billions, of years through the cold between the stars. Scientists have watched carefully, and what they have found is both familiar and entirely new. The first discoveries came from the telescopes that found it. The Atlas survey, which constantly scans the sky for near-Earth objects, detected a faint moving point of light that did not fit the pattern of known asteroids or comets. When the trajectory was calculated, it became clear that this object was not from our solar system. Its path was hyperbolic, which means its speed and direction are such that the Sun's gravity cannot hold it. As more telescopes focused on it, they began to build a clearer picture. The comet displayed a visible coma, a hazy envelope of gas and dust surrounding the nucleus. Even at a large distance from the Sun, the comet was already active. That is a sign that some of its ices, especially carbon dioxide, can sublimate at low solar heating. This early activity allowed astronomers to study the composition B. One of the first major measurements was the detection of water vapor. Using ultraviolet spectroscopy, astronomers observed the signature of hydroxyl radicals. These radicals are produced when sunlight breaks apart water molecules in the coma. From this, they inferred the water production rate. Even at more than 3 astronomical units from the Sun, the comet was producing tens of kilograms of water every second. This means that its surface must have R. Infrared spectroscopy added another layer to the story. Space-based telescopes and sensitive ground instruments revealed strong signals of carbon dioxide. The ratio of carbon dioxide to water is much higher than what is typically seen in solar system comets. This indicates that the comet either formed in a region rich in carbon dioxide or that its structure preserved these ices more effectively during its interstellar journey. A high carbon dioxide content. The James Webb Space Telescope played a crucial role in the investigation. Its instruments observed the comet's coma and tail in infrared wavelengths, where the signatures of different ices and dust components can be seen clearly. Webb's observations confirmed that carbon dioxide dominates the gas coma, with water, carbon monoxide, and other trace gases also present. These measurements provide clues about the temperature and pressure conditions in the comet's original formation environment, long before it was ejected from its home system. Visible light observations told another part of the story. The comet appears redder than many known comets. This is measured through its spectral slope, a quantity that shows how brightness changes with wavelength. The higher slope means the reflected sunlight from the comet's dust is more intense at longer wavelengths. This redness can be due to organic materials, space weathering, or differences in grain size and composition. Polarimetry measurements, which study how light is polarized when it scatters off dust, revealed an unusual pattern. Most comets show a certain range of polarization depending on the angle at which they are viewed. This comet, however, has a deeper and narrower negative polarization branch. That means the light becomes more polarized in a negative direction at small phase angles, more so than typical comets. This suggests differences in the dust grain surfaces or structures, perhaps more compact or differently shaped grains than those found in many solar system comets. These clues, taken together, tell scientists that this object did not form under the exact same conditions as most comets in our solar system. Its high carbon dioxide content, redder spectral color, and unusual polarization signature point toward an origin in a colder or chemically distinct protoplanetary disk. It might have come from the outer regions of another star system, where carbon dioxide ice is stable and plentiful, or from a disk that had different elemental abundances. Another discovery is the stability of its orbit. Careful measurements show little non-gravitational acceleration so far. Many comets show slight deviations in their trajectory due to jets of gas pushing unevenly on the nucleus. In this case, the absence of a strong non-gravitational effect suggests either that the comet is outgassing symmetrically or that its nucleus is massive and dense enough to resist being nudged noticeably. This gives astronomers confidence in predicting its path far in advance. As the comet moves closer to the Sun, astronomers expect its activity to increase. More sunlight means more sublimation, and more sublimation means a denser coma, and possibly a longer tail. Observations during perihelion will be critical. Telescopes will watch for changes in brightness, structure, and composition. Sudden outbursts, fragmentation events, or unexpected behavior are always possible, especially for interstellar objects whose st. This is not just a chance to study another comet. It is a rare opportunity to study the building blocks of another planetary system. Every molecule that boils off the surface and every grain of dust drifting in the coma carries information about the place where this comet was born. By studying these materials, scientists can compare them with our own solar system and learn how similar or different other star systems might be. The data already gathered has sparked theories. Some scientists suggest that high carbon dioxide content could mean the comet originated in a colder disk, maybe farther from its parent star than most of our comets did. Others wonder whether interstellar radiation exposure altered its outer layers, preserving deeper volatiles by forming a crust that traps heat differently. Some speculate that its dust may contain organic molecules that formed under different cosmic conditions, offering clues about the chemical diver. Every measurement brings new questions. How long has it been traveling through interstellar space? How did it get ejected from its home system? Was it flung out by the gravitational pull of giant planets, as many objects in our own system are? How long did it wander before crossing paths with the Sun? These questions are still open, but with each observation the picture sharpens. The next months will be crucial. As the comet moves closer to perihelion, observatories around the world and in space will monitor its brightness curve, coma evolution, and tail dynamics. Instruments aboard Mars orbiters will watch as it passes closer to Mars than to Earth. If activity spikes, they may detect changes in the coma structure and chemistry almost in real time. This steady collection of data will continue until long after the comet swings past the Sun and begins its slow departure back into the galactic dark. The results will enrich our understanding of interstellar objects and give astronomers a rare, precious look at material that formed around another star. This is why scientists are excited. This is why the comet matters. Theories and speculations about its origin and journey. Every comet carries a story locked inside its ice and dust. For most comets in our solar system, that story begins in the cold outskirts of the protoplanetary disk, in places like the Kuiper Belt and the Oort cloud. For this comet, the story begins in another star system entirely. It is a true wanderer. Scientists have spent years preparing for moments like this, when an object from the interstellar medium crosses our neighborhood, bringing foreign material and foreign history. Theories about its origin are many, and each tries to answer one simple question: where did this comet come from? One of the leading ideas is that this comet was born in the outer regions of a young planetary system around another star. In the earliest stages of star and planet formation, disks of gas and dust surround young stars. In those disks, particles clump together, ices condense, and small icy worlds begin to form far from the warmth of the central star. If large planets form inside these disks, their gravity can fling smaller objects outward. Many comets in our own Oort cloud were likely launched there by the gravitational tugs of Jupiter and Saturn. In the same way, this interstellar comet could have been ejected from its home system by massive planets orbiting its star. Over time it would drift away, slowly escaping the gravitational pull of its star and joining the population of free-floating objects between the stars. Another theory focuses on the chemical fingerprint of the comet. The high abundance of carbon dioxide compared to water suggests that it may have formed in a region colder than where many of our comets formed. Carbon dioxide requires lower temperatures to remain frozen, so a high carbon dioxide content hints at an origin in a cold, distant zone of its original protoplanetary disk. This could mean that the star it formed around was smaller or cooler than our Sun, producing a colder disk. It could also mean that the comet formed at a greater distance from its star, perhaps tens of astronomical units away. Some scientists suggest that the comet may have been altered during its long journey through interstellar space. Out there, far from any star, the object would have been exposed to cosmic rays and ultraviolet radiation for millions of years. These high-energy particles can change the surface chemistry, producing organic molecules and creating a hardened crust on the surface that traps the volatiles inside. This crust might explain some of the unusual polarization and color measurements. A long exposure to interstellar radiation can darken and redden the surface, just as old surfaces on icy bodies in our own solar system become dark and red over time. There are even speculations that this comet could have been wandering for a very long time, perhaps since the earliest eras of our galaxy. Some models suggest that once an object is ejected from its system, it can spend hundreds of millions or even billions of years drifting. Its orbit through the galaxy might have taken it past several spiral arms, through regions dense with stars and regions of empty interstellar space. It may have experienced close passes with other stars, weak gravitational tugs, and changes in its trajectory over immense spans of time. By the time it arrived here, its journey might have been unimaginably long, a slow drift through the galaxy's quiet spaces. Another theory considers the possibility of its ejection mechanism. In some star systems, gravitational interactions can be far more chaotic than in our own. A system with multiple giant planets can easily eject smaller icy bodies. If two or more massive planets have resonances or unstable orbital arrangements, their gravitational fields can slingshot comets outward at high velocities. The eccentricity of this comet's orbit and its speed indicate that it received a powerful gravitational push long ago. Some scientists wonder whether binary stars might play a role. Binary systems are common in the galaxy. If the comet formed in a disk around a binary pair, the combined gravitational influences could be even more efficient at ejecting comets. Binary systems can fling material outward in complex patterns, and some simulations show that they may produce many interstellar comets. A few speculative ideas reach further. There are discussions about whether interstellar comets could carry material that might seed other star systems. The idea is not that this comet brings life, but that dust grains and organic molecules might be transferred from one system to another by such wandering bodies. Over cosmic timescales, these comets could distribute the raw ingredients of planets and chemistry across the galaxy. They might contribute to the mixing of material between stellar neighborhoods. The comet's current path tells part of its story as well. Its speed relative to the Sun is high, and its direction points toward a region of the sky that scientists can trace backward. By calculating its incoming trajectory, they can guess which part of the galaxy it came from. However, because of gravitational perturbations from stars and clouds over its long journey, the trail becomes uncertain if you look back far enough. Beyond a certain point in the past, the uncertainties in galactic models mean we cannot say exactly which star it came from. Another interesting line of thought concerns its internal structure. Some scientists propose that interstellar comets may be more compact and cohesive than typical solar system comets. If they are strong enough to survive ejection and long periods of exposure to interstellar radiation, they might develop hardened exteriors and dense interiors. This could explain why this comet shows stable outgassing and little non-gravitational acceleration. A strong nucleus would be less prone to asymmetric jets that change its orbit. Others think that its high carbon dioxide content might make its behavior unusual near perihelion. Carbon dioxide sublimates at lower temperatures than water, so much of the activity we see may come from carbon dioxide jets. This could cause subtle differences in how the coma looks and how the tail evolves as it approaches and leaves perihelion. There are theories about fragmentation too. Some comets fragment as they near the Sun because of thermal stress or internal pressure from gases. Scientists are watching closely for signs of cracking or splitting. If the comet breaks apart, its fragments could reveal layers of pristine material that have been sealed away since it formed. Fragmentation would also change the coma's appearance dramatically, possibly creating multiple bright knots of activity. A more speculative but fascinating idea involves the galactic distribution of such comets. If every planetary system ejects large numbers of comets during its formation, then the galaxy must contain a vast population of these wandering bodies. Most never pass close to stars, but a tiny fraction will cross the solar system. Each one offers a unique chance to learn about the conditions in distant star systems. This comet is only the third interstellar object ever detected, which means our ability to observe such objects is still new. As surveys become more sensitive, many more might be discovered in the coming decades. There is also a cultural and philosophical side to these theories. Some astronomers and thinkers reflect on the idea that these comets are messengers from other suns. They carry information about places we cannot visit, and they travel without intention, guided only by gravity. Their journeys are vast and slow, indifferent to time as we measure it. This comet's appearance reminds us that the galaxy is not static. Material moves, drifts, and exchanges between systems. The solar system is not isolated. It is part of a larger galactic community where ice and rock wander freely. The theories about its journey and origin continue to evolve as new data comes in. Each observation either supports or challenges some part of these ideas. Over time, as astronomers gather more information, some theories will become stronger and others will fade. The comet itself does not tell us its story in words, but through light, chemistry, and motion. Scientists translate these silent messages into human understanding, piece by piece. What we can expect in the coming months. The comet is still far from the inner solar system, drifting slowly closer along its calculated path. Each day the sunlight grows a little stronger, the solar wind grows a little more intense, and the icy surface begins to respond in ways that astronomers can anticipate but not fully predict. The months ahead will be a time of careful watching, of patient listening to the silent changes taking place on the surface of this interstellar wanderer. The first expectation is a gradual increase in brightness. As the comet moves closer to the Sun, more sunlight reaches its nucleus. This added warmth causes ices to sublimate at a higher rate, which creates a denser coma and can extend the tail. Carbon dioxide sublimation will likely dominate in the early stages, since carbon dioxide can turn into gas even at relatively low temperatures. This phase may already be underway, but it will become more pronounced as the comet approaches 1.5 astronomical units from the Sun. In the weeks before perihelion, astronomers expect to see a measurable increase in activity. The coma should grow larger and brighter, and telescopes may detect new structures forming in the tail. These structures might include jets of gas and dust that stream from specific regions on the surface, arcs and fans created by rotating active areas, and waves in the tail caused by interactions with the solar wind. Ground-based telescopes equipped with high-resolution imaging will monitor these developments, and space telescopes will collect spectra to track changes in chemical composition. Mars will be a key observation point. As the comet passes relatively close to Mars, orbiters around the planet will have a unique vantage point. Instruments aboard Mars orbiters can watch the coma and tail from a different angle than Earth-based observatories. They can also detect subtle variations in the coma density and structure. This will allow scientists to measure the composition of the gas more accurately, and to watch how the comet responds to the solar environment as it nears perihelion. Rovers on the Martian surface may not see the comet directly, but data relayed from orbiters will enrich the overall picture. As perihelion approaches in late October, scientists will be particularly alert for sudden outbursts. Comets sometimes undergo rapid changes in activity as trapped gases find new escape paths or as structural weaknesses give way. An outburst can increase brightness dramatically for a short time, and it can produce fresh jets or fragments. Such events are unpredictable but not uncommon. Observatories are prepared to catch them if they occur, coordinating around the world to avoid gaps in coverage. If the comet remains stable, its perihelion passage will be a smooth curve of rising activity followed by a gradual decline as it moves away from the Sun. The closest approach to the Sun is not especially near compared to some comets that dive close to the solar surface, but it is close enough to drive significant sublimation. After perihelion, as the comet moves outward again, the activity will wane, the coma will thin, and the tail will gradually fade into the background of space. One of the key scientific opportunities during this time will be to study how the composition of the coma evolves with changing solar distance. The ratios of different gases may shift as different ices sublimate at different rates. For example, if the comet contains layered regions with different volatile compositions, the inner layers may become active later, revealing new spectral signatures. This can tell scientists about the internal structure of the nucleus and how the ices are arranged beneath the surface. Dust studies will also be important. As activity increases, more dust is released, and this dust interacts with sunlight and the solar wind. By measuring the way the dust reflects light and polarizes it, scientists can infer the size, distribution, and composition of the grains. Comparing these measurements before and after perihelion can reveal whether the comet sheds different kinds of dust as it evolves. Another expectation is that astronomers will refine their understanding of the nucleus size and shape. As the coma becomes denser, it may seem harder to see the nucleus directly, but changes in brightness and coma structure can offer indirect clues. If the nucleus is irregularly shaped or has distinct active regions, the rotation of the comet will modulate the brightness in a periodic way. By tracking these variations over time, astronomers can estimate the rotation period and possibly even infer something about the shape of the nucleus. For amateur astronomers with powerful telescopes, this period will offer the best chance to observe the comet visually. It will not become bright enough to see with the naked eye, but under dark skies and with sensitive instruments, the coma and a faint tail might be visible. These observations, while not as precise as professional data, can contribute valuable timing and brightness information to the global observation campaign. After perihelion, the comet will begin its outbound journey. This phase is often quieter but still important scientifically. As the comet cools, different parts of the nucleus may shut down at different rates. Some areas may continue to outgas for longer periods, especially if they contain more volatile ices. Observing how quickly the activity declines can provide information about the thermal properties of the nucleus and the distribution of active areas. Eventually, the comet will fade from view as it moves farther away from both the Sun and Earth. But the data collected during its approach and perihelion passage will continue to be analyzed for years. Each spectrum and image contains details about composition, structure, and evolution. Scientists will compare this data with that of other comets, both interstellar and solar system-borne, to see where this object fits in the broader picture of small bodies in the galaxy. There is also the possibility of unexpected events. Comets have surprised astronomers many times in the past. Fragmentation, sudden shifts in activity, or unusual tail behavior can occur with little warning. The interstellar nature of this comet adds an extra layer of uncertainty because its internal structure and strength may not match the patterns familiar from local comets. Scientists remain open to surprises, ready to adjust their models and observations if something unexpected happens. For the broader public, this period is a reminder that the universe is dynamic. A small icy traveler from another star system is passing through, and while it poses no danger, it offers a moment to reflect on the vastness of space and the quiet ways in which different worlds can intersect. Even though this comet will not blaze across our skies, its journey is extraordinary. It carries ancient ices that formed around another star. It moves on a path that has taken it through the cold galaxy for ages, and for a brief moment it passes through our neighborhood. The coming months are not just about scientific measurements. They are also about patience, curiosity, and the simple wonder of watching something rare. The comet approaches steadily, indifferent to our attention, but our gaze follows it, capturing every photon, decoding every whisper of its ancient story. The long journey beyond the Sun. As the comet swings past perihelion and begins its slow retreat from the Sun, a new phase of its story unfolds. The intense sunlight that awakened its icy surface gradually weakens, the pressure of solar radiation lessens, and the once active jets of gas and dust begin to fall silent one by one. The coma thins, the tail length shortens, and the interstellar traveler resumes the quiet pace that carried it through the darkness between the stars. Its journey is far from over. In truth, this is only a brief interlude in a voyage that spans unimaginable distances and timescales. The first weeks after perihelion are a period of transformation. The comet has endured the heat of its closest approach, and the surface has changed. The volatile ices near the surface have been depleted, leaving behind a layer of dust, rocky fragments, and possibly hardened crusts formed by repeated cycles of sublimation and freezing. Some regions may remain active for a time, especially where deeper layers of ice are exposed, but overall the activity begins to wane. Telescopes that once tracked a brightening coma now observe a gradual fading, as the gas production rate drops and the dust disperses into space. This fading is not uniform. Some areas of the nucleus may retain pockets of more volatile materials that continue to outgas at low levels even as the comet moves farther from the Sun. These lingering jets can produce small, localized comae that persist for months. By studying how these features evolve, astronomers can learn about the layering of ices within the nucleus and how thermal waves penetrate the surface. The pattern of lingering activity can reveal differences between shallow and deep ice deposits, hinting at the comet's formation environment long ago. As the comet retreats, its orbit begins to stretch out into the depths of the solar system once more. Because this object is on a hyperbolic trajectory, it is not gravitationally bound to the Sun. Unlike periodic comets that return again and again on elliptical paths, this visitor will continue outward and eventually leave the solar system entirely. Its velocity is great enough to overcome the Sun's gravitational pull, and once it passes beyond the influence of the major planets, it will resume its interstellar journey. The outbound path carries it past the orbits of the outer planets, though at distances too vast for any close encounters. Jupiter's gravitational influence has already played its role during the inbound leg, slightly altering the trajectory but not enough to capture the comet or deflect it toward a collision course. Saturn, Uranus, and Neptune lie far off to the sides of its path, exerting only minor perturbations. By the time the comet crosses Neptune's orbit, it will have faded to invisibility even in the largest telescopes. Yet astronomers will continue to track its position as long as possible, using precise astrometric measurements to refine its orbit. Each observation helps improve models of its trajectory, ensuring that future generations will know exactly where this interstellar traveler went after its brief visit. These measurements also allow scientists to detect any slight non-gravitational accelerations caused by remaining outgassing. Even weak jets can produce tiny changes in velocity over long times, and these changes can reveal details about the comet's remaining activity and shape. As it travels outward, the comet will enter regions of space where the Sun is just another bright star in the background. The solar wind grows weaker, the sunlight diminishes to a faint glimmer, and the temperature drops again to the deep cold of interstellar space. Any remaining activity will eventually cease entirely, leaving the nucleus as a silent, frozen remnant surrounded by a faint halo of dust. It will drift on, following its hyperbolic path into the galaxy, just as it once did before entering our solar system. The future trajectory of the comet is a matter of orbital mechanics and galactic dynamics. Once it is fully beyond the solar system's gravitational sphere of influence, its path will be determined by the combined gravitational fields of the stars and clouds in the galaxy. Over millions of years, small tugs from passing stars and molecular clouds will gently bend its course. It may wander through spiral arms, passing near other star systems, perhaps even becoming visible to civilizations elsewhere as a faint visitor in their night skies. This long interstellar voyage is a reminder of how dynamic and interconnected the galaxy is. Small icy bodies like this comet are not confined to their birthplaces. They can be ejected from their home systems through gravitational interactions, then spend eons drifting through the galaxy, occasionally passing through other systems as silent messengers from distant stars. This comet may have been traveling for millions or even billions of years before entering our solar system. Its ices preserve a record of the conditions in the region where it formed, long before our Sun was born. When it finally leaves our solar system, it will do so without fanfare. There will be no bright display, no dramatic departure visible to the naked eye. It will simply fade into the darkness, unseen but not forgotten. Scientists will carry the data they gathered during its passage, and those data will continue to yield insights long after the comet itself is gone. The chemical composition, the orbital details, and the observed behavior will become part of the collective knowledge of how interstellar objects behave when they encounter a new star system. In the far future, the comet may pass near another star and perhaps be captured into a new orbit, beginning a new chapter in its existence. Or it may continue drifting through the galaxy indefinitely, never settling, always moving, a silent wanderer in the vast darkness. There is no way to predict its ultimate fate, because the galaxy's gravitational landscape is constantly shifting. Each stellar encounter adds a new twist to its path, and over millions of years, these small changes accumulate into unpredictable outcomes. The departure of this comet also offers scientists a valuable opportunity to refine their models of interstellar object dynamics. By observing how its path changes under the influence of solar gravity and planetary perturbations, and by comparing these changes with models, they can improve predictions for future visitors. The more interstellar comets and asteroids we observe, the better. For now, the comet's journey beyond the Sun is both an ending and a continuation. It marks the end of its brief, brilliant chapter within our solar system, but it also continues the far longer story of its travels through interstellar space. Its path is a thread woven into the immense tapestry of galactic motion, connecting distant regions and times in ways we are only beginning to grasp. As it fades into the distance, the sense of quiet wonder remains. A traveler from another star came, passed close enough for us to notice, shared a glimpse of its ancient icy heart, and then moved on, indifferent to our curiosity yet forever part of our cosmic story. The night sky holds many such mysteries, and this comet is a gentle reminder that the universe is not static. It is alive with movement, with journeys that span unimaginable scales, with encounters that bridge the gap between stars. The mystery of the comet's birthplace. Before it entered our solar system, long before its ices began to sublimate under the warmth of the sun, this comet had already lived through an ancient and distant history. It was not born in the darkness between the stars. It came from somewhere, from a stellar nursery where dust and gas gathered, where planets and icy bodies formed, and where gravitational encounters cast some objects out into the void. The comet's composition, structure, and motion are like a coded message, hinting at the nature of its birthplace and the events that sent it on its journey. Astronomers believe that most interstellar comets are fragments of planetary system formation. When a young star is surrounded by a disk of dust and gas, countless small icy bodies form beyond the region where temperatures are low enough for volatile compounds to condense. These icy bodies are similar to the comets in our own solar system, which formed in the outer regions beyond the giant planets. Over time, as planets grow and migrate, their gravity disturbs the orbits of these smaller bodies. Many are scattered outward, some into elongated orbits within their home systems, and some are ejected entirely, gaining enough velocity to escape into interstellar space. This ejection process can produce trillions of wandering objects over the lifetime of a galaxy. Most of them will never encounter another star system closely enough to be observed. But a few, like this comet, happen to pass near a star and fall inward on a hyperbolic path, giving astronomers a rare glimpse of material formed in distant environments. By studying their composition, scientists can compare the building blocks of different planetary systems and learn how common or diverse the processes of planet and comet formation are across the galaxy. One of the first clues to the comet's origin lies in its chemical makeup. Observations have revealed an unusually high ratio of carbon dioxide to water in its coma. In our solar system, most comets contain both CO2 and H2O, but typically water dominates when they are close to the Sun. This comet, however, shows a CO2 to H2O ratio around 8:1, which is significantly higher than most local comets. This suggests that the region where it formed was extremely cold enough for CO2 to freeze and remain stable over long periods. Such conditions are usually found in the outermost reaches of a planetary disk, far beyond T. The presence of CO and other volatiles also provides hints. These molecules are more volatile than water, meaning they can sublimate at lower temperatures. If the comet retains significant amounts of them, it likely formed in a region shielded from intense radiation and remained in deep freeze for most of its history. This aligns with the idea that it originated in the cold, outer parts of its home system, possibly in a region analogous to our Kuiper belt or even an extended Oort cloud. Another clue comes from its color and the properties of its dust. The reddish spectral slope and unusual polarization behavior suggest a surface coated with complex organic molecules and fine dust grains processed by cosmic radiation over immense timescales. In interstellar space, objects are bombarded by high-energy particles and ultraviolet radiation, which gradually alter the chemical structure of surface materials. Simple ices can transform into more complex compounds, including long-chain carbon molecules that impart a reddish hue. This processing indicates that the comet spent a very long time exposed to the interstellar environment after being ejected from its birthplace. The question of when and how it was ejected is also fascinating. Ejection typically occurs during periods of dynamical instability in a planetary system. For example, if giant planets migrate through a disk of small bodies, their gravity can fling some objects inward and others outward. the outward scattered objects may gain enough velocity to escape entirely. This process likely happened in our own solar system when Jupiter and Saturn migrated, creating a scattering event that shaped the outer regions of the solar system and filled the Oort cloud with icy bodies. Something similar must have happened in the comet's home system, perhaps involving giant planets, or even interactions with passing stars in a dense stellar cluster. Some theories suggest that the comet could have been ejected relatively early in its system's history, perhaps only a few million years after formation, and has been wandering the galaxy ever since. Others propose it might have been ejected more recently, depending on the age and evolution of its parent star. Without knowing its exact velocity vector relative to the local standard of rest in the galaxy, it is difficult to trace it. Nevertheless, astronomers attempt to match its incoming direction and velocity with the motions of nearby stars to see if any might have been close enough in the past to have ejected it. This is a complex task because stars move through the galaxy at different speeds and directions, and their relative positions change over time. So far, no definitive stellar birthplace has been identified, but studies continue. If its velocity and direction could be linked to a known star that was nearby a few million years ago, it would provide a remarkable insight into the history of another planetary system. The very fact that such objects exist tells us that planetary system formation and evolution are dynamic processes, not isolated events. Every star likely ejects countless icy bodies during its lifetime. The galaxy is filled with a vast unseen population of these wanderers, drifting silently through the void. Occasionally, one of them happens to pass through our solar system, and we get a chance to study it. Each one carries information about its origin, preserved in its icy heart and dusty surface. This comet's journey from its birthplace to our solar system is a story of gravitational interactions, cosmic radiation, and deep time. It may have formed billions of years ago, been ejected soon after, and traveled through interstellar space for an epoch before crossing paths with the Sun. In that time, entire civilizations could rise and fall, stars could be born and die, and galaxies could shift their shapes. Yet the comet endures, a small but durable fragment of cosmic history, unchanging except for the slow accumulation of radiation processing. By studying objects like this comet, scientists hope to build a comparative picture of planetary system formation. If interstellar comets show similar compositions to our own, it would suggest that the processes that built our solar system are common throughout the galaxy. If they show large differences, it might reveal a diversity of planetary architectures and chemical environments far greater than we imagined. Either outcome is profoundly important for understanding our place in the cosmos. As it moves away from the Sun and back into the cold darkness, the clues about its origin remain locked within it. We can only piece together fragments from remote observations, interpreting its spectrum, its activity, and its orbit. But even these fragments tell a story rich with cosmic history, a story that connects our solar system to distant stars and ancient events across the galaxy. The future of encounters with interstellar visitors. The arrival of this comet is not an isolated event. It is part of a larger story that stretches across the history of the solar system and extends far into the future. The galaxy is vast and filled with countless wandering objects, and our solar system moves through this cosmic sea like a ship through quiet but crowded waters. Sometimes, by pure chance, one of these travelers crosses our path. The comet is one such example, but it will not be the last. In the years and centuries ahead, many more interstellar objects will pass through our neighborhood, some too faint to notice, others bright enough to draw attention from telescopes across the world. Scientists believe that interstellar comets and asteroids constantly drift through the galaxy, and our solar system encounters them regularly. Most are small, perhaps only a few meters or tens of meters across, and they pass unnoticed. But occasionally, a larger body like this comet enters the inner solar system, giving us a rare opportunity to observe material formed around other stars. These encounters are windows into other worlds, offering information we could never obtain otherwise. Each visitor carries with it a record of its distant birthplace, locked in its composition and structure, and by studying them we expand our understanding of planetary systems beyond our own. The discovery of Oumuamua in 2017 was the first clear sign that interstellar objects can and do pass through our solar system. It was followed by the detection of the interstellar comet Borisov in 2019, which provided the first chance to observe an active comet from another star. Now this comet continues the story, and its detailed study is refining our understanding of how these objects behave. The growing list of interstellar visitors suggests that such encounters are not rare at all, but rather inevitable over time. As telescopes improve and sky surveys become more sensitive, the number of detected interstellar future surveys, especially those conducted by large wide-field telescopes, will likely discover dozens or even hundreds of such objects over the coming decades. Each discovery will add a new piece to the puzzle, revealing the diversity of materials, structures, and histories these wanderers carry. Some may be rocky and inert, resembling asteroids. Others may be rich in ices and display active comets and tails as they approach the Sun. Some might be large enough to study in great detail, while others might be tiny fragments barely visible except in the deepest exposures. The probability of one of these objects approaching Earth closely depends on their number density in the galaxy and the geometry of their orbits. Most will pass at great distances, far beyond the orbit of Earth, but over long timescales, close approaches are statistically certain to happen. The solar system has existed for billions of years, and during that time it must have experienced countless such passages. Some may have even collided with planets or moons in the distant past, delivering exotic material from other star systems. It is possible that fragments of interstellar comets already lie buried in the geological record of Earth, unrecognized for what they are. One of the most exciting possibilities is that future missions might be able to intercept and study these visitors up close. Rapid response spacecraft, designed to launch quickly after detection, could rendezvous with a passing object and collect data or even samples. Such a mission would allow scientists to examine interstellar material directly, revealing details about its composition, structure, and isotopic ratios that cannot be obtained from telescopic observations alone. Concepts for such missions are already being developed, including fast interceptors equipped with powerful propulsion systems and autonomous navigation. The challenge lies in the fact that interstellar objects travel extremely fast relative to the Sun, often tens of kilometers per second, and their trajectories are only discovered after they enter the solar system. This leaves a short window for mission planning and launch. But advances in propulsion, on-orbit manufacturing, and autonomous spacecraft control may make such missions feasible in the future. If successful, they would represent one of the most profound scientific achievements of our time, allowing humanity to study the building blocks of distant planetary systems without leaving our own. These encounters also carry a deeper significance. They remind us that our solar system is not isolated. We are part of a dynamic galaxy where material is constantly exchanged between stars. Over billions of years, comets and asteroids are ejected from their home systems, wander through interstellar space, and occasionally pass through other systems, including ours. This exchange of material may even play a role in the spread of complex molecules or the ingredients for life. Some scientists speculate that interstellar objects could transport prebiotic compounds between star systems, a process that might contribute to the emergence of life in multiple places across the galaxy. From a long-term perspective, encounters with interstellar objects may offer opportunities and challenges for future civilizations. Advanced spacefaring societies might deliberately intercept and harvest such objects for scientific study or as sources of raw materials. The ices and organics contained in comets could provide fuel, water, and building blocks for deep space missions. Their high velocities might make them useful for slingshot maneuvers or even as transport vehicles if they can be redirected or harnessed. Conversely, close approaches by large interstellar bodies could pose impact risks that would need to be monitored and managed, just as we track potentially hazardous asteroids today. The comet currently passing through our solar system is a quiet visitor, posing no threat and offering a wealth of scientific information. But its presence reminds us that the future will bring more such encounters. Some will be studied from afar, some may be intercepted by probes, and some might pass by without anyone noticing. The galaxy is alive with movement, and our solar system is part of that cosmic dance. For now, scientists continue to refine their models, improve detection systems, and prepare for the next visitor. Each new object is a chance to test our understanding, to learn something new about the universe, and to be reminded that we are part of a vast interconnected galactic community. The story of this comet is one chapter in that ongoing saga, and many more chapters remain unwritten. Throughout history, humanity has gazed at the night sky and wondered about the wandering lights that move differently from the stars. Comets have always stirred both fear and fascination. In ancient times, they were often seen as omens, heralding change, disaster, or new beginnings. Today we understand their nature more clearly, but their presence still awakens something deep in the human imagination. When an interstellar object enters our solar system, it carries not only its icy nucleus and dusty tail, but also the weight of stories, possibilities, and questions that stretch far beyond our everyday world. Interstellar comets like this one remind us that our planet is not isolated in space. The solar system is constantly exposed to a slow rain of cosmic material, some of it from other stars. Over the vast span of Earth's history, impacts from interstellar objects, though rare, are almost inevitable. The probability of a direct collision during any given century is extremely low, but across hundreds of millions of years, the odds grow. A single large impact could alter Earth's environment in profound ways, just as impacts from local asteroids and comets have done in the past. Imagine a time long before humans appeared, when the planet was still young and evolving. A large interstellar object could have entered the solar system, unnoticed by any living creatures, and impacted the Earth or another planet. Such an event would deliver material unlike any native to the solar system, perhaps containing exotic isotopic ratios, unusual ices, or organic molecules formed in distant stellar nurseries. These ingredients might have mixed with Earth's atmosphere, oceans, and crust, becoming part of the geological and biological record in subtle but lasting ways. Some scientists speculate that interstellar objects might have played a role in delivering complex organic molecules to young planets. The building blocks of life, such as amino acids and nucleobases, can form in the icy mantles of dust grains in interstellar space and survive within comets for immense periods of time. If such molecules were carried to Earth by impacts or even by gentle atmospheric entry of smaller fragments, they might have contributed to the chemical richness that eventually led to the emergence of life. This idea fits within broader theories of panspermia, which suggests that the ingredients for life, or even microbial life itself, could spread between star systems. Beyond physical impacts, interstellar comets also influence our understanding of planetary history through the information they carry. By analyzing their composition, we gain indirect insights into the diversity of chemical environments in the galaxy. If we find similarities between the ices and organics in interstellar comets and those in local comets, it suggests that the processes that produce life's raw materials on Earth may be widespread. If we find stark differences, it may reveal alternative pathways by which planetary systems evolve and develop chemical complexity. Either outcome deepens our understanding of Earth's place in the cosmos. Interstellar visitors also spark human imagination in unique ways. Each new discovery inspires stories, theories, and dreams about distant worlds and cosmic journeys. The idea that an object could travel across the galaxy for millions of years and then briefly pass through our skies connects us to a scale of time and space that is almost beyond comprehension. Writers, artists, and thinkers have long drawn inspiration from comets, imagining them as harbingers of change, carriers of messages, or vehicles for alien travelers. Even today, when we study these objects with telescopes and scientific instruments, they continue to inspire a sense of mystery and wonder. The arrival of the Oumuamua in 2017 triggered a wave of speculation. Its unusual shape, lack of a visible coma, and odd acceleration led some scientists and many members of the public to consider exotic explanations, including the possibility of artificial origin. While natural explanations remain the most likely, the discussion itself showed how quickly interstellar visitors can capture human imagination. This current comet, with its bright coma and clear cometary behavior, has not generated the same level of mystery about its nature, but it has still become a focus of scientific attention and curiosity. In the future, as detection technology improves, we may discover interstellar objects more frequently and earlier in their approach. This will allow more detailed studies and perhaps even direct exploration. Each discovery will bring new opportunities to learn about the galaxy and new fuel for the imagination. People may begin to think of the galaxy not as a distant abstract concept but as a connected network of star systems linked by drifting icy messengers. Interstellar objects also offer a unique perspective on time. Their journeys last for millions or even billions of years. While human civilizations rise and fall in mere centuries, these objects travel through space largely unchanged, carrying within them records of ancient events and distant environments. Observing them is like finding a time capsule from another part of the galaxy, delivered by chance into our celestial neighborhood. They remind us of the continuity and vastness of cosmic history, of the fact that our brief moment in time is part of a much larger story. On Earth, these encounters can influence culture as well as science. Each new comet brings a wave of public interest, scientific activity, and creative expression. In ancient times, such appearances inspired myths and legends. In modern times, they inspire documentaries, books, art, and sometimes lively debates about the origins of life and the possibility of interstellar communication. They also serve as powerful educational moments, drawing people's attention to astronomy and the wonders of the universe. The influence of interstellar visitors on human thought may grow in the coming centuries as we learn more about them. Future generations may view these objects not only as scientific curiosities but as familiar travelers in a galaxy we are beginning to explore. Spacefaring civilizations might track them routinely, visit them, harvest their resources, or even hitch rides on their trajectories to reach other star systems. In this way, what today seems like a distant and mysterious event could become a practical part of humanity's interaction with the galaxy. Even now, as this comet passes silently through the solar system, it is shaping our understanding of the universe. The data gathered by telescopes will feed into scientific papers, inspire new theories, and perhaps influence future space missions. Its presence in the night sky, though faint, is a reminder that we are part of a galaxy alive with motion and history. The scientific legacy and galactic lessons. The study of this comet is more than just an isolated scientific endeavor. It is part of a growing legacy, a slow and patient construction of knowledge about the galaxy and the forces that shape it. Every interstellar visitor that passes through our solar system brings with it a fragment of a story written far away and long ago. By observing these visitors carefully, astronomers are building a mosaic of evidence that will eventually give us a clearer picture of how planetary systems form, evolve, and interact across the Milky Way. When this comet was first detected, astronomers immediately began recording its position night after night, measuring its changing brightness, its coma structure, and its spectral signature. Each observation added another piece to the puzzle. These measurements are archived in global databases, allowing future scientists to revisit the data, apply new analytical methods, and extract further insights long after the comet has faded into the darkness. The legacy of this observation campaign will endure for decades, perhaps centuries, as part of humanity's accumulated knowledge of the cosmos. One of the key lessons from studying interstellar comets is the diversity of planetary systems. By comparing their compositions to those of solar system comets, scientists can infer how similar or different their birth environments were. The chemical ratios of volatiles like water, carbon dioxide, carbon monoxide, and more complex organic molecules act as fingerprints. If these fingerprints resemble those found in our own solar system, it suggests that the processes of icy body formation are universal across many star systems. If they differ significantly, it hints at a rich variety of environments and histories scattered throughout the galaxy. Another important legacy involves understanding the frequency and distribution of interstellar objects. By tracking how many such visitors we detect over time, and their sizes and trajectories, astronomers can estimate how many are drifting through the galaxy. This provides indirect information about how efficiently planetary systems eject material during their formation and evolution. It also helps refine models of galactic dynamics, since the paths of these objects are influenced by the gravitational pull of stars, molecular clouds, and the overall structure of the Milky Way. Interstellar comets are also probes of the interstellar medium itself. As they travel between stars, they are bombarded by cosmic rays and interstellar dust, slowly altering their surfaces. By analyzing their physical properties, scientists can infer the nature of the environments they pass through. The reddening of their surfaces, the depletion or retention of certain ices, and the presence of radiation-processed organics all tell us about the density, temperature, and radiation levels in different parts of the galaxy. This turns each comet into a traveling data recorder, carrying a record of its long interstellar journey. The study of these objects also drives technological and methodological innovation. Detecting and tracking faint, fast-moving interstellar visitors requires powerful telescopes, sensitive detectors, and advanced computational tools. The growing interest in these objects has accelerated the development of automated sky surveys, rapid response observation networks, and new analytical techniques. These advances benefit not only the study of comets, but many other fields of astronomy as well. Each new discovery pushes the boundaries of what our instruments and methods can achieve. On a galactic scale, the presence of interstellar comets highlights the interconnectedness of planetary systems. Each star is not an isolated island but part of a complex network of exchanges, where gravitational interaction sends small bodies drifting across stellar neighborhoods. Over billions of years, this exchange may mix the outer layers of planetary systems, spreading dust, ices, and organic molecules far and wide. In this way, the Milky Way functions almost like an ecosystem, where material circulates between its many components, creating a shared chemical heritage that links distant stars. Understanding this galactic circulation has profound implications for our view of cosmic evolution. It suggests that the formation of planets and the distribution of life's ingredients are not confined to isolated systems, but are part of a larger galactic process. Interstellar comets act as both messengers and participants in this process. By studying them, we gain insight into how stars and planets contribute to and are shaped by the wider galactic environment. The scientific legacy of this comet will also include its role as a benchmark for future discoveries. As more interstellar objects are detected, scientists will compare their properties to this one, building a classification system and identifying patterns. Over time, this will allow astronomers to group interstellar objects into categories based on their composition, activity, and trajectory. Such classifications may reveal underlying structures in the population, such as common origins, preferred ejection mechanisms, or links to specific types of stellar systems. Beyond the strictly scientific legacy, there is a philosophical and cultural dimension. Studying interstellar visitors forces us to think on timescales and distances that dwarf human history. It connects us to the vast flow of matter through the galaxy, reminding us that Earth is part of a much larger cosmic story. The comet is not just a point of light in the sky, it is a physical connection between our solar system and distant, unknown worlds. it carries memories of another place and time, preserved in ice and dust, and by studying it we become part of that story. Future generations will likely look back at these early studies as the beginning of a new era of galactic exploration. Long before humanity ventures to other stars, we are already learning about them indirectly through these wandering messengers. The knowledge gained from this comet and others like it will shape how we understand our galaxy, how we design future missions, and how we think about our place in the universe. As this comet continues its journey outward, leaving behind the sun's warmth, its scientific legacy remains anchored here on Earth. In observatories, data archives, research papers, and the minds of scientists, the story continues. The lessons it teaches us about chemistry, dynamics, galactic structure, and cosmic history will endure long after the comet itself has vanished into the deep dark beyond. The distant future and the age of interstellar navigation. As we look far ahead into the future, long after the comet has vanished into the darkness, it becomes clear that the knowledge we are gathering today is not merely for curiosity. It is laying the groundwork for something much greater. Humanity's understanding of interstellar comets may one day play a central role in how we navigate, explore, and perhaps even inhabit the galaxy. These icy wanderers are more than fleeting visitors. They are natural signposts scattered across the interstellar void, potential stepping stones for future explorers. Imagine a distant era when humanity has developed technologies that allow it to travel between the stars. In this future, spacecraft are no longer limited to the solar system but sail through the galaxy on journeys lasting decades or even centuries. In such a scenario, interstellar comets could serve as beacons. Because their trajectories are predictable and recorded, they can act as navigation markers, much like stars and lighthouses once guided ships across Earth's oceans. Future starfarers could plan their routes using the positions and paths of these comets, ensuring they remain oriented as they cross the silent depths between stellar systems. These comets might also serve as vital way stations. Their icy nuclei are rich in water and other volatiles, which can be harvested for life support and propulsion. A spacecraft reaching an interstellar comet could anchor itself, extract water, convert it into breathable oxygen and hydrogen fuel, and then continue its journey. In this way, comets become cosmic refueling stations, scattered naturally throughout the galaxy. Such a network would make interstellar travel more sustainable, reducing the need to carry vast quantities of resources from the point of origin. There is also the possibility that some interstellar comets contain valuable scientific records within their cores. Having spent millions or even billions of years drifting through different regions of the galaxy, they may preserve trapped particles, cosmic rays, and isotopes that act like time capsules. Future explorers could drill into their interiors to retrieve this ancient galactic memory, piecing together a detailed record of environments far from their current location. Each comet would offer a unique perspective, like a chapter in a vast cosmic chronicle. In this distant future, it is not hard to imagine that entire missions could be based around intercepting and studying such comets up close. Swarms of robotic probes could be dispatched to rendezvous with incoming objects as soon as they are detected, attaching themselves like barnacles to study the comet as it passes through the solar system. Some probes might even hitch a ride, using the comet's momentum to journey outward to the stars. This passive method of interstellar travel could be the first step before humans themselves venture into interstellar space. Advanced civilizations might also use comets for deliberate purposes. They could alter the paths of these objects, steering them toward desired destinations, perhaps even using them as slow but massive carriers of materials. Over long timescales, a civilization could build an interstellar infrastructure of redirected comets, creating a network of resources and stations stretching between stars. This would be a subtle, patient form of engineering, unfolding over millennia, using natural celestial bodies as tools rather than relying entirely on artificial structures. The presence of redirected or altered comets in a distant star system could even serve as a signature of advanced life. Just as astronomers today search for unusual patterns in light that might indicate alien technology, future scientists might look for improbable cometary trajectories that suggest deliberate control. Anomalous patterns of movement among interstellar objects could be one of the clearest indicators of intelligent activity on a galactic scale. Beyond their practical uses, interstellar comets might become symbols of cultural significance in this future. Just as ancient sailors followed the stars and built myths around their motions, future space-faring civilizations might weave stories around these icy wanderers. They could become markers of journeys, symbols of connection between distant star systems, and reminders of the shared galactic heritage of all worlds. As humanity spreads outward, the understanding of cometary dynamics will become a fundamental science, much like navigation and astronomy were for seafaring civilizations on Earth. Pilots and navigators of future starships may study charts of cometary paths, learning to interpret their positions and predict their future locations with precision. Knowledge that began with careful telescopic observations in the early 21st century could one day guide ships through interstellar space. It is also conceivable that human settlements could form around some of these comets. In deep space, far from any star, a sufficiently large icy body could provide a foundation for a habitat. By hollowing out parts of its nucleus and installing artificial light and heat sources, settlers could create self-sustaining communities shielded from cosmic radiation by thick layers of ice. The water and volatiles would provide the raw materials for life support, agriculture, and industry. These wandering settlements would drift slowly through the galaxy, following the comet's natural trajectory, becoming mobile outposts of civilization. Such habitats would not be bound to any single star but would instead inhabit the spaces between them, thriving in the cold and dark. They would be truly nomadic societies, living on celestial bodies that were once seen only as passing visitors. Over time, these communities might develop unique cultures shaped by their isolation and by the rhythm of their comet's journey through the galaxy. The very same object that astronomers once tracked through telescopes could become home to future generations of interstellar travelers. The role of interstellar comets in this distant future is a reminder of how knowledge accumulates and transforms. What begins as a point of light in the night sky, analyzed by scientists for clues about the galaxy, can eventually become a cornerstone of practical exploration and cultural meaning. By studying these objects carefully now, we are planting the seeds for a future in which they play a vital role in humanity's cosmic journey. In this vision of the far future, the comet is no longer a fleeting visitor. It is a companion, a resource, a guide, and a bridge between worlds. It is a testament to the power of curiosity and patience, showing how even the most distant and transient phenomena can shape the destiny of a species that dares to dream beyond its home star. The comet's endless journey into the galactic night. Once the comet completes its brief passage through the inner solar system, it begins a new and silent chapter. Pulled by the same gravitational forces that first sent it drifting toward our star, it now follows its outbound trajectory, heading back into the cold depths of interstellar space. From the point of view of Earth, it will gradually grow dimmer, shrinking to a faint dot and eventually fading completely from sight. But this disappearance is not the end of its story. For the comet itself, this is merely the continuation of a voyage that has already lasted for millions or perhaps billions of years, and may continue for countless more. As it travels farther from the sun, the last remnants of solar warmth quickly dissipate. The jets of gas and dust that once streamed from its surface fade away as the volatile ices freeze solid again. The glowing coma collapses, the tail evaporates into nothingness, and the nucleus returns to its dormant state, a dark and silent wanderer surrounded by the infinite quiet of space. There is no sound out here, only the soft, invisible whisper of radiation and the occasional distant pulse of a star. The journey ahead will take the comet into regions where stars are sparse and the night is unimaginably deep. Between the spiral arms of the galaxy lie vast stretches of space where light from nearby stars is faint and scattered. In these interarm voids, the comet may spend millions of years without encountering anything significant. Its orbit will be subtly shaped by the collective gravitational field of the Milky Way, bending and curving along a vast, invisible path determined by the galaxy's mass distribution. Occasionally, the comet may pass near a star. If the encounter is close enough, the gravitational influence of that star could alter its trajectory, changing its speed, direction, or eccentricity. Such encounters are rare but inevitable over long timescales. A single close pass near a massive star could send the comet veering toward a new region of the galaxy, or even trap it temporarily in a loose orbit before slinging it away again. These stellar flybys act like cosmic currents, slowly redirecting the comet over the eons. The comet's surface will continue to change subtly as it travels. High-energy cosmic rays constantly bombard it, slowly breaking down chemical bonds and creating new complex organic molecules on its surface. Over time, the outer layers may darken and harden, forming a tough crust that protects the interior ices from further alteration. Dust grains in interstellar space may also collide with it at high velocities, pitting its surface with tiny craters and leaving a record of its journey etched into its crust. It may pass through regions filled with diffuse interstellar clouds, where gas and dust are more abundant. In these zones, a thin layer of material could settle onto the comet, coating it with new compounds and subtly altering its mass and reflectivity. Each encounter leaves its mark, a faint trace of the places it has been. Like an ancient traveler collecting souvenirs from distant lands, the comet gathers layers of galactic history on its surface as it drifts. Time for the comet is measured not in years or centuries, but in millions of orbits around the galactic center. The Milky Way rotates slowly, taking hundreds of millions of years to complete a single revolution. During that time, the comet may circle the galaxy many times, crossing spiral arms, gliding through voids, and weaving its path through the gravitational tapestry created by billions of stars. One day, far in the future, the comet might approach another planetary system. Perhaps it will pass through the outskirts of a young star surrounded by a disk of gas and dust. Its arrival could disturb the orbits of comets and planetesimals in that system, triggering cascades of movement and collisions. Or perhaps it will be drawn inward, briefly illuminated again by the warmth of another sun, shedding a new tail as alien eyes watch it streak across unfamiliar skies. For the comet, the identities of the systems it visits do not matter. It is a patient traveler, indifferent to the dramas of the worlds it passes. It is also possible that the comet will eventually escape the Milky Way entirely. A close encounter with a massive star or a passing giant molecular cloud could give it enough velocity to break free from the galaxy's gravitational grip. If that happens, it would continue its journey into intergalactic space, heading into the dark ocean between galaxies. Out there, the distances are even more immense, the stars fewer and farther apart, and the night even deeper. It might drift forever, untouched and unseen, a solitary relic of a distant civilization's night sky. Yet even in such desolate spaces, the comet remains part of the grand galactic story. It carries with it the materials from which stars and planets are made, the frozen gases and dust grains forged in ancient stellar furnaces. Its nucleus holds records of its birth environment, the cosmic rays it encountered, and the collisions it endured. It is a messenger without a destination, silently bearing information across the cosmos. From a human perspective, this journey is almost beyond comprehension. Civilizations will rise and fall, stars will be born and die, spiral arms will shift, and still the comet will continue on its path. Its persistence is a reminder of the vastness and timelessness of the universe, where human history is a brief flicker and cosmic journeys stretch across ages unimaginable to us. Astronomers sometimes imagine what it would be like if an advanced civilization encountered this comet in the far future. Perhaps they would study it carefully, tracing its origins back to our solar system. They might find ancient isotopic signatures that point to the sun's birthplace, reconstructing a story of a time and place long vanished. In that sense, the comet becomes not just a traveler, but a messenger carrying a fragment of our cosmic identity to distant corners of the galaxy. This endless journey has no final destination, only a continuous path shaped by chance encounters and galactic forces. The comet will keep drifting, silent and cold, a solitary thread in the vast cosmic fabric. It does not seek meaning, but through its journey, it gives meaning to our attempts to understand the universe. It is both transient and eternal, fleeting in the sky yet end. Humanity's emotional bond with the wanderers of the stars. Throughout history, humanity has looked up at the night sky and felt something difficult to put into words. A mix of awe, curiosity, fear, and wonder has accompanied every glimpse of a comet's glowing tail, or the sudden appearance of a bright visitor in the heavens. Long before telescopes, long before science could explain orbital paths and icy nuclei, people saw these travelers as omens, as messengers, as mysterious lights crossing the fixed constellations. Even now, in an age of advanced astronomy and precise calculations, that feeling has not entirely faded. There remains a quiet magic in watching a comet appear, tracing its slow arc across the stars, knowing that it has come from far away and will soon disappear again. The emotional bond between humanity and these wanderers begins with their unpredictability. Most celestial bodies, like stars and planets, follow paths that are regular and familiar. They rise and set at expected times, their motions charted and repeated year after year. Comets, however, arrive unexpectedly. They emerge from the darkness, grow brighter night after night, and then vanish again, often never to return in a human lifetime. This fleeting nature makes them feel alive, like visitors with stories to tell. When a comet appears, people notice. Ancient civilizations often recorded these appearances in their chronicles, associating them with great events or changes. Some saw them as harbingers of disaster, others as signs from the gods. Even in more recent centuries, their sudden presence could stir entire communities to gather outside at night, pointing upward, watching together in silence. There is a shared sense of witnessing something rare and cosmic, something beyond the control or influence of human life. For modern observers, the emotions are different but no less powerful. Knowing that a comet has traveled for millions of years to reach us only heightens the sense of wonder. It is like receiving a message from across time and space. The faint glow in the sky represents a journey through regions we will never visit, past stars and clouds we cannot see. When we look at it, we are not just seeing a frozen ball of dust and ice. We are glimpsing a traveler that connects distant parts of the galaxy, a thread that ties us to places we cannot imagine. There is also something deeply humbling about comets. Their sheer scale of movement and time reminds us of our smallness. A single comet may have existed long before humanity evolved and may continue its journey long after our civilizations have faded. Against that backdrop, our individual lives and even our collective history feel brief. But rather than diminishing us, this perspective can bring a sense of peace. It reminds us that we are part of something vast and enduring, and that the universe carries on its grand rhythms regardless of human concerns. For many people, watching a comet can also be a meditative experience. Standing beneath the night sky, away from city lights, letting the silence of the stars settle around you, the slow movement of the comet becomes like a celestial lullaby. Its presence encourages quiet reflection, drawing the mind outward toward cosmic distances and inward toward personal thoughts. This is why comet appearances often linger in people's memories for decades. They are moments when time seems to stretch, when the ordinary world fades and the infinite reveals itself gently above us. Artists, poets, and storytellers have long been inspired by comets. They appear in myths, paintings, songs, and literature as symbols of change, mystery, destiny, and cosmic beauty. Their rarity and brilliance make them natural metaphors for fleeting moments of significance in human lives. Some cultures saw them as celestial messengers, others as travelers between worlds, and others still as embodiments of divine will. Across all these interpretations runs a common thread: comets are seen not just as objects but as characters in the grand story of the sky. Even today, in the scientific era, this storytelling continues. Each newly discovered comet receives a name, an identity. Astronomers speak of its behavior, its brightness, its outbursts, as if describing a living being. When a comet breaks apart, there is often a tone of sadness in the reports, as though a great traveler has met an untimely end. When one grows unexpectedly bright, excitement spreads rapidly, mirroring the thrill of spotting a long-awaited visitor arriving unexpectedly at the gates. Interstellar comets like this one evoke an even deeper emotional response. They are not merely returning visitors from the outskirts of our own solar system but strangers from beyond, carrying with them the mystery of unknown origins. Their presence makes the galaxy feel more connected, as if invisible paths exist between distant stars, and for a brief moment, one of those paths has intersected our sky. People gather in fields, on rooftops, or at observatories, bundled in blankets against the night air, staring upward in silence. Some bring telescopes, others just their eyes. Children ask questions. Adults fall quiet. Cameras click, but often the most powerful moments are those when no one speaks, when the comet hangs above the horizon and the vastness of the night presses gently down. In those moments, the comet becomes more than an astronomical object. It becomes a bridge between the human heart and the cosmos. Its light touches both the outer edges of the galaxy and the quiet corners of our thoughts. It is a reminder of mystery, of journeys without end, of the beauty that appears and then fades, leaving behind only memory and wonder. This emotional connection may explain why comets have been remembered long after they've vanished. People pass down stories of the great comets they saw as children. Astronomical societies publish drawings and notes. Artists paint their long glowing tales over dark landscapes. Centuries later, historians read these records and feel a connection to those who stood under the same sky long ago. In this way, comets become threads linking generations, weaving human history together through shared moments of awe. The bond between humanity and these wanderers is quiet but enduring. It is born from a mix of science, story, and emotion. As long as people look up at the night sky, comets will continue to inspire wonder. They remind us that we live in a universe filled with travelers, that our world is not isolated but part of a vast, moving cosmic sea. And when one appears, drifting silently across the stars, we pause, look up, and feel that ancient connection once more. Sparks of curiosity and the birth of new discoveries. Every time a comet appears, something happens in the scientific community that goes far beyond simply observing another celestial object. Comets have a way of igniting curiosity, of pulling researchers, students, and amateur stargazers alike into a shared pursuit of knowledge. They are both familiar and mysterious, predictable in their general behavior but full of surprises in their details. When a comet like 3I Atlas sweeps into view, it does more than offer a spectacle. It opens doors to new questions, new methods, and sometimes entirely new fields of exploration. The moment a comet is discovered, a quiet race begins. Telescopes across the world swing toward its coordinates, and observation schedules are rearranged. Scientists know that time is precious. A comet changes rapidly as it approaches the Sun, and every day can bring new phenomena to record. Spectroscopic instruments begin analyzing the light it reflects and emits, searching for signatures of different gases and organic compounds. Photometric measurements track its brightness changes. High-resolution imaging studies the shape and behavior of its coma and tail. All of this information is gathered and shared at astonishing speed, creating a network of data that connects observatories on different continents. For many scientists, this is a moment of inspiration. A new comet often brings with it the chance to test new instruments or refine techniques that have never before been applied to such an object. Students working on their first research projects may find themselves analyzing data from a newly discovered comet, contributing directly to real scientific progress. The arrival of such a visitor can shape entire careers, providing opportunities for young astronomers to publish their first papers and make meaningful contributions to the field. Comets like 3I Atlas, which originate from interstellar space, push this curiosity even further. They do not follow the usual patterns of local comets, and their compositions may differ in subtle but revealing ways. Each new measurement provides clues about the environment in which the comet formed, perhaps around a star very different from our Sun. The mere existence of such a comet raises profound questions about the processes that shape planetary systems across the galaxy. How common are these objects? How far do they travel? How often do they visit other stars? Each observation brings us closer to answering these questions, but each answer seems to give rise to more mysteries. Technological innovation often follows in the wake of such discoveries. Detecting faint interstellar comets requires sensitive, wide-field surveys capable of scanning the sky continuously. This need drives improvements in detectors, optics, and data processing algorithms. When a new comet is found, these technologies are put to the test, refined, and pushed beyond their previous limits. Lessons learned from tracking one visitor feed back into the design of future telescopes, ensuring that the next discovery will be captured with even greater clarity. The presence of an interstellar comet also encourages collaboration on a global scale. No single observatory can follow a rapidly moving object continuously, but by coordinating observations around the world, scientists can track it almost without interruption. This collaboration often brings together professionals and amateurs, experts in spectroscopy, imaging, and orbital mechanics, and specialists in different regions of the electromagnetic spectrum. The result is a kind of scientific symphony, with each group contributing their part to create a complete picture of the comet's behavior. Sometimes, unexpected discoveries emerge from these campaigns. A comet may display unusual outbursts, or its trajectory may reveal unexpected gravitational influences. Spectral analysis might uncover molecules that have rarely been observed before. A small detail noticed in one data set can trigger follow-up observations that lead to breakthroughs in understanding not just comets, but the broader cosmic environment. The curiosity sparked by these icy wanderers has a way of branching outward, leading researchers into new areas they might not have explored otherwise. Interstellar comets, in particular, challenge our models of how material moves through the galaxy. Their presence forces scientists to refine theories about the ejection of debris from planetary systems and the structure of galactic space. Each newly detected object provides constraints on how frequently stars fling comets into interstellar space, how they survive their long journeys, and how they eventually encounter other systems. These insights ripple through multiple fields of astrophysics, influencing everything from studies of star formation to models of galactic dynamics. Beyond professional science, comets spark public curiosity as well. News of a bright comet often spreads rapidly, drawing people outside to look up. Amateur astronomers bring out their telescopes and share views with neighbors and communities. Astronomy clubs host events, schools organize viewing nights, and people who rarely think about space find themselves staring at the sky with renewed interest. For some, this is the beginning of a lifelong fascination with astronomy. Many scientists can trace their career choice back to a single night spent gazing at a comet as a child. This cycle of curiosity and discovery is one of the most powerful aspects of comet appearances. A distant, icy object drifts into the inner solar system, and suddenly thousands of minds are engaged in understanding it. Technologies are improved, collaborations are formed, careers are launched, and new insights are gained. All of this is triggered by a traveler that neither knows nor cares about our attention, yet inspires it nonetheless. Comets remind us that discovery often begins with a moment of wonder. A small point of light appears where there was none before. Questions arise. Instruments are pointed. Data flows. The mysteries of the universe draw us forward, just as they have for centuries. And each time we peel back a layer of the unknown, we find not an end, but a new horizon. The appearance of 3I Atlas and others like it is part of a long tradition of curiosity. Ancient sky watchers wondered about these lights. Early scientists struggled to understand their orbits. Modern astronomers analyze their spectra and trajectories. Future generations may visit them directly. Through it all, the spark remains the same, a feeling that there is something worth knowing out there, something beautiful, something waiting to be understood. Cosmic ingredients and the origins of life. Every comet that enters the inner solar system carries with it more than dust and ice. Hidden within its fragile structure are the raw ingredients that shaped the earliest chapters of planetary evolution. These cosmic travelers are like frozen archives, preserving the materials from which stars and planets were born billions of years ago. For scientists, each new comet is not merely an object to observe but a potential key to understanding the story of life itself. When Earth was young, its surface was hot, chaotic, and constantly bombarded by debris from the surrounding solar system. Asteroids, meteoroids, and comets crashed down relentlessly, delivering both destruction and essential materials. Among the most important of these were water and organic compounds. Many researchers believe that a significant portion of Earth's water may have originated from icy bodies similar to 3I Atlas. These comets formed in cold, distant regions where ice remained stable for billions of years, far from the heat of the sun. When they ventured inward, they carried that frozen water with them, releasing it as vapor when heated. Over time, countless impacts may have contributed to the filling of our planet's oceans. But water alone does not create life. More intriguing is the discovery that comets contain complex organic molecules. Spectroscopic studies of several comets have revealed the presence of amino acids, carbon chains, alcohols, and other building blocks that are essential for biological processes. These are not signs of life themselves, but they are the kinds of molecules that, under the right conditions, can assemble into the structures needed for living systems to emerge. The idea that comets seeded the early Earth with these compounds is known as panspermia, and while it remains a hypothesis, the evidence continues to grow. An interstellar comet like 3I Atlas adds a fascinating twist to this story. Unlike typical comets that formed in the same protoplanetary disk as Earth, interstellar comets originated around other stars. Their compositions might reflect entirely different chemical environments. If such objects can bring organic molecules from one star system to another, then the ingredients for life may be shared across vast galactic distances. This raises profound questions. Could the seeds of life be drifting silently through space, waiting to find a hospitable world where they can flourish? Could life on Earth owe its origins, at least in part, to materials carried from distant stars? To explore these questions, scientists study cometary dust and gas with great precision. When a comet passes close enough, spacecraft and ground-based observatories can measure the relative abundances of hydrogen isotopes in its water. By comparing these ratios to those found in Earth's oceans, researchers can determine whether a particular comet type might have contributed to our planet's water supply. Similar studies of organic compounds help identify whether the molecules found in comets match those formed through known chemical pathways in interstellar space. Each measurement provides another piece of the puzzle. The Rosetta mission to Comet 67P revealed just how complex comet chemistry can be. Instruments detected a surprising variety of organic molecules, some of which had never before been observed on such a body. This discovery suggested that comets are active chemical laboratories, where sunlight and cosmic rays drive reactions within their icy nuclei. Over millions of years, these reactions can produce molecules of increasing complexity. When these comets impact young planets, they deliver not only the raw materials but also chemical systems already in motion, potentially giving a head start to the emergence of life. Interstellar comets might represent even more diverse laboratories. Formed in different environments, exposed to different stellar radiation fields, and shaped by their unique journeys through space, their chemical inventories may contain surprises we have not yet imagined. Observing objects like 3I Atlas gives scientists rare opportunities to test theories about the universality of chemical processes in the galaxy. If similar organic molecules are found in comets from many different systems, it suggests that the conditions for life's ingredients are widespread. This would strengthen the idea that life might not be unique to Earth but a natural outcome of cosmic chemistry. The study of cometary materials also connects to questions about the timeline of life's origins. Fossil evidence shows that life appeared on Earth relatively quickly after the planet became habitable. This rapid emergence suggests that the necessary ingredients and conditions were already in place. Comets, constantly bombarding the early Earth, may have provided those ingredients continuously, enriching the planet's surface with water and organics. Over time, as conditions stabilized, these materials could have assembled into self-replicating molecules, leading to the first primitive life forms. Interstellar visitors like 3I Atlas broaden this narrative beyond our solar system. They suggest that the exchange of materials between stars may be a common galactic process. Planetary systems do not form in isolation. They are part of dynamic stellar neighborhoods where gravitational interactions can fling icy bodies into interstellar space. Some of these travelers eventually encounter other systems, carrying with them molecular signatures of their birthplaces. This cosmic exchange could mean that the ingredients of life are constantly circulating through the galaxy, linking distant worlds in subtle ways. For a moment, imagine 3I Atlas not merely as a chunk of ice and rock, but as a messenger from another star. It has traveled for millions or perhaps billions of years, crossing light years of empty space. Along the way, it has endured cosmic rays, distant starlight, and the slow erosion of time. Yet within it, some molecules have remained preserved, unchanged since the days of its formation. As it approaches our solar system, sunlight awakens these ancient compounds, releasing them into space. Some drift outward, some fall inward, and some may eventually be captured by Earth's atmosphere, joining our planet's vast reservoir of cosmic material. These quiet interactions are easy to overlook, but they are part of a grand and intricate story. Comets like 3I Atlas are not just visitors to our skies. They are carriers of history, chemistry, and possibility. Their journeys remind us that life's story may be written not on one world alone, but across the fabric of the galaxy itself. Each comet is a thread in that tapestry, connecting distant regions and epochs in ways that we are only beginning to comprehend. Shapers of worlds and architects of change. Long before planets settle into quiet orbits and develop stable climates, the early stages of any solar system are shaped by violent encounters. Clouds of dust and gas collapse to form stars, and the remaining material gathers into swirling disks where planets, asteroids, and comets gradually take shape. In this chaotic environment, comets play a far more active role than their delicate, icy appearances might suggest. They are dynamic agents of change, capable of altering planetary histories through their movements, impacts, and gravitational influences. When a solar system is young, countless icy bodies orbit its central star in distant, cold regions. Over time, gravitational nudges from giant planets scatter these bodies inward. Some crash into planets, others are ejected into interstellar space, and a few settle into stable distant orbits, forming vast reservoirs such as the Oort cloud. This scattering process is not random. Each encounter leaves a mark. Massive impacts can reshape planetary crusts, stir up atmospheres, and even trigger climate shifts that last for millennia. On Earth, comets have played a double role as both destroyers and bringers of renewal. Large impacts release tremendous amounts of energy, equivalent to millions of nuclear explosions. They can vaporize oceans, ignite global fires, and throw debris high into the atmosphere, blocking sunlight for years. Such events can drive mass extinctions, resetting the evolutionary clock. Yet at the same time, comets have delivered water, organics, and minerals that replenish the surface and create opportunities for new life to emerge. In this way, they act as cosmic sculptors, erasing old landscapes and helping shape new ones. Consider a single impact event. A comet perhaps several kilometers wide approaches a young planet. As it enters the atmosphere, it heats up rapidly, creating a brilliant streak across the sky. Moments later, it strikes the surface at tens of kilometers per second. The impact unleashes a shockwave that travels through rock and water alike, carving out craters that can stretch for hundreds of kilometers. Molten rock splashes outward, debris rains down across continents, and atmospheric gases mix with vaporized material to create temporary chemical hazes. Over geological timescales, these impacts become part of the planet's topography, visible as scars that tell the story of its past encounters. Comets have also been catalysts for planetary evolution in more subtle ways. When they approach a star, their icy surfaces sublimate, releasing gas and dust into space. This material forms enormous, glowing tails that can stretch for millions of kilometers. Some of the dust lingers in orbit, forming belts or clouds that scatter starlight and influence the temperature of the surrounding environment. Over time, this dust can settle onto planetary surfaces, altering their albedo and contributing to climate regulation. Even a steady drizzle of microscopic cometary particles can accumulate into significant layers over millions of years, leaving chemical fingerprints in rocks and ice cores. On worlds without thick atmospheres, comet impacts can directly shape the landscape. Mars, for example, bears the marks of ancient bombardments that sculpted its surface. Many of its craters likely originated from cometary bodies. These impacts may have temporarily released buried water or triggered geothermal activity, creating brief warm periods that could have allowed liquid water to flow. Such events, though short-lived, may have influenced the planet's potential habitability in ways scientists are still uncovering. Giant planets like Jupiter act as powerful gravitational gatekeepers in this process. Their immense mass bends the paths of comets, sometimes capturing them into temporary orbits, sometimes flinging them outward, and sometimes sending them toward the inner solar system. Jupiter in particular has shielded Earth from countless potential impacts by absorbing or redirecting incoming comets. Observations of fragments of comet Shoemaker-Levy 9 colliding with Jupiter in 1994 revealed the incredible scale of these events. Each impact created plumes larger than Earth itself, demonstrating how a single comet can unleash planetary-level energy. In other planetary systems, similar dynamics likely play out. Comets may migrate inward during the early stages, delivering water to dry, rocky planets. They may also influence the formation of atmospheres by contributing volatile compounds. A world that forms too close to its star may lose its water early, but a later influx of comets from the outer system could restore its oceans. Conversely, excessive bombardment might strip atmospheres away or destabilize climates, making planets less hospitable. The balance between these effects is delicate, and every system has its own history. Interstellar comets like 3I Atlas remind us that these processes are not confined to single systems. Some comets are ejected entirely, becoming wanderers between stars. Over immense timescales, they may encounter other systems and influence them in turn. A passing interstellar comet could collide with a planet, contribute material to a protoplanetary disk, or subtly alter the orbits of outer bodies through gravitational interactions. In this way, comets link stellar systems into a web of exchanges, where the evolution of one world may be influenced by the debris of another. For a moment, imagine looking down on a young planetary system from far above. The star glows at the center, surrounded by whirling disks of gas and dust. Comets streak inward on elongated paths, like messengers bearing ancient cargo. Some plunge toward the star, disintegrating in bright flares. Others strike young planets, sculpting their surfaces and delivering water. Still others are caught in gravitational dances with giant planets, flung outward toward the dark. Over millions of years, These interactions create the stable architecture we observe today, with planets following predictable orbits and reservoirs of comets. This grand choreography is still happening in our own solar system. The Oort cloud and Kuiper belt contain countless comets, remnants from the era of planetary formation. Occasionally, gravitational tugs send one of these ancient objects inward, giving us a brief glimpse of the processes that shaped our world long ago. Interstellar visitors like 3I Atlas provide an even rarer window into how these dynamics play out across the galaxy, offering clues about the shared history of planetary systems. As we study these cosmic travelers, we gain insight not only into their nature but also into the forces that have shaped every world we know. Comets are not passive relics. They are active participants in the ongoing story of planetary evolution. Through impacts, migrations, and exchanges, they have helped shape the destiny of worlds, including our own. Mapping the path of a wanderer. The journey of a comet through the cosmos may appear spontaneous and mysterious, but its trajectory follows the elegant rules of celestial mechanics. Every movement is shaped by gravity, velocity, and the subtle influences of nearby bodies. To understand how close a comet like 3I Atlas might come to us, scientists turn to mathematics, telescopes, and long chains of careful observation. These methods transform distant specks of light into precise predictions, revealing where the comet has been, where it is now, and where it may travel in the future. When 3I Atlas was first detected, astronomers focused on collecting as many positional measurements as possible. Each observation fixed the comet's location against the background stars, and over time, these points traced out a curved path. From just a few of these positions, skilled orbital calculators can begin to determine the shape of its orbit. Interstellar comets differ from typical solar system comets in a key way. Their orbits are hyperbolic, meaning they do not circle the Sun in closed loops but instead pass through once and continue onward into deep space. This shape arises because their velocity exceeds the Sun's gravitational binding speed, allowing them to escape its pull after their brief visit. The orbital elements of a comet define its trajectory. These include its inclination, which describes the tilt of its path relative to the solar system's plane, its perihelion distance, which is the closest point to the Sun, and its eccentricity, which indicates how stretched the orbit is. For hyperbolic visitors, the eccentricity is greater than 1. By combining these elements, astronomers can build a three-dimensional model of the comet's journey. In the case of 3I Atlas, early calculations showed that it entered the solar system from a high inclination angle, traveling on a steep, elongated path that originated far beyond the edges of the Oort cloud. Once the basic orbital model is established, astronomers refine it using more observations. Small uncertainties can lead to large differences in long-term predictions, so repeated measurements over weeks and months are essential. Each data point narrows the error bars and improves the accuracy of future position estimates. Specialized software integrates these data with gravitational influences from all major planets, modeling how their pulls subtly adjust the comet's course. Even a small nudge from Jupiter or Saturn can alter its trajectory significantly over time. Another factor that must be considered is non-gravitational acceleration. When a comet approaches the Sun, sunlight heats its surface, causing jets of gas and dust to erupt. These outgassing jets act like miniature thrusters, pushing the comet slightly off its gravitational path. For long-period comets, these effects can be minor, but for smaller or more active ones, the jets can noticeably change their direction. In the case of interstellar comets, scientists must pay close attention to these accelerations because their unfamiliar compositions might lead to unexpected behaviors as they warm. By combining gravitational models with outgassing effects, astronomers can project a probable trajectory for months or even years ahead. These projections are expressed as a set of possible future paths, often visualized as a narrow cone spreading outward from the comet's current position. The width of this cone reflects the uncertainty of predictions, and as more data are collected, the cone narrows. For 3I Atlas, Early trajectory models suggested that while it would pass through the solar system at a high velocity, its closest approach would keep it at a comfortable distance from Earth, far beyond any collision risk. Probability plays an important role in these calculations. Instead of predicting a single future position, scientists generate a cloud of potential paths based on uncertainties in the data. By simulating thousands of scenarios with slightly varied initial conditions, they determine the likelihood of different outcomes. For Earth impact probabilities, this means calculating how many of these simulated paths intersect with Earth's orbit. Even if the chance is extremely low, it must be quantified carefully. Fortunately, for known comets like 3I Atlas, the probabilities of impact are extraordinarily small, often near zero for the foreseeable future. However, the story does not end with Earth. Astronomers also calculate potential close approaches to other planets and to the Sun itself. Some comets pass close enough to Jupiter to be dramatically deflected, altering their future trajectories. Others may skim the Sun so closely that they either fragment or experience powerful outbursts. For interstellar visitors, these interactions are brief but significant. A single close pass near a giant planet can shift their hyperbolic trajectory slightly, changing the direction they exit the solar system and potentially sending them on a different path through the galaxy. Trajectory calculations also allow astronomers to trace a comet's path backward in time. By running simulations in reverse, they can determine the direction from which the comet arrived, offering clues about its origin. For 3I Atlas, backward integration suggested that it came from deep interstellar space, with no obvious parent star identified. Its long journey likely began when gravitational interactions in its home system ejected it into interstellar space millions or even billions of years ago. Since then, it has wandered silently, passing through empty regions until its path intersected ours. These orbital studies are not merely academic exercises. They are essential for planetary defense, for planning spacecraft missions, and for understanding the broader structure of our galactic neighborhood. A precise orbit allows scientists to schedule telescope observations during key moments, to target spacecraft flybys, and to assess any future risks. In the case of 3I Atlas, the knowledge that its trajectory poses no threat allows scientists to focus on studying its properties rather than worrying about potential impacts. Imagine a giant cosmic map, with stars, planets, and comets moving along intricate paths. Each object follows the pull of gravity, weaving through space in a silent dance that has been ongoing for billions of years. Comets like 3I Atlas are guests in this dance, arriving unexpectedly, tracing elegant arcs past the Sun, and then vanishing once more into the dark. Our ability to map their paths with precision is a triumph of human curiosity and mathematics, transforming distant wanderers into well-understood travelers. As telescopes become more powerful and detection networks more sophisticated, we can spot these visitors earlier and track them more accurately. Each one offers a glimpse of the wider galactic environment, revealing the hidden structure of the universe beyond our solar system. The path of 3I Atlas is one such thread, a faint line on a vast cosmic chart that connects distant regions through the quiet motion of a single comet. Calculating cosmic probabilities. Every comet that sweeps through our solar system brings with it a set of questions. Where did it come from? What path will it follow? And most crucially, how close will it pass to Earth and other planets? These questions are answered not through guesswork but through detailed calculations, blending mathematics, physics, and astronomical observations into careful forecasts. For a visitor like 3I Atlas, scientists rely on these methods to estimate the probability of future approaches, even decades or centuries ahead, though the object will likely not linger in our neighborhood for long. The process begins with a foundation of orbital data. Each observation contributes to a growing record of positions and velocities, forming the backbone of any probability calculation. Because 3I Atlas is moving on a hyperbolic trajectory, it is not bound to the Sun. This simplifies some aspects of prediction, since it will not loop back for repeated encounters, But it also means that small uncertainties can grow rapidly as the comet races away into interstellar space. To keep these uncertainties manageable, astronomers prioritize collecting data during the comet's closest approach period, when it appears brightest and is easiest to track with high precision. Once this data is gathered, scientists generate a set of initial conditions that reflect the measurement uncertainties. Instead of relying on a single calculated orbit, they create a statistical ensemble of slightly varied orbits. Each variation represents a plausible real trajectory based on the limits of observational accuracy. Using powerful computers, they then propagate these orbits forward in time, integrating the gravitational interactions of all major solar system bodies and sometimes even considering perturbations from smaller objects if necessary. The result is a cloud of simulated future positions. For each future date, scientists can plot where the comet is likely to be, represented by a fuzzy region of probability that grows larger over time. This expansion happens because even tiny differences in velocity or position can lead to large deviations after months or years. For long-period and interstellar comets, this cloud spreads out rapidly as they move away from the Sun, reflecting the decreasing precision of predictions. The key metric of interest is the minimum orbit intersection distance, often shortened to MOID. This value measures how closely the comet's trajectory comes to intersecting Earth's orbit. If the MOID is large, the probability of a close approach or impact is effectively zero. If it is small, scientists pay closer attention. A low MOID does not guarantee a collision, but it indicates that under certain timing conditions, a close encounter could happen. For 3I Atlas, current calculations show that its MOID is comfortably large, meaning there is no foreseeable risk of impact with Earth. However, MOID is not the only factor. Timing plays a crucial role. Even if a comet's path crosses Earth's orbit, Earth must be at the same point at the same time for an encounter to occur. Because both the comet and Earth move along their respective orbits, this timing window is usually very narrow. Astronomers calculate the probability that both objects will occupy the same region of space simultaneously. For most comets, including interstellar ones like 3I Atlas, this probability remains vanishingly small. Another technique involves Monte Carlo simulations. In this method, scientists run thousands or even millions of slightly different orbital scenarios, each with randomly varied initial conditions within observational uncertainties. For each scenario, the computer checks whether a close approach or impact occurs. By counting the number of scenarios that lead to close encounters and dividing by the total number of runs, researchers estimate the probability of such events. This approach is especially useful for objects with poorly constrained orbits, or when looking far into the future, where uncertainties grow large. For 3I Atlas, the results of such analyses are reassuring. Its high velocity and hyperbolic orbit mean that it will pass through the solar system quickly and then continue outward, making only a single visit. Its closest approach distance remains far outside Earth's orbital path, and its trajectory is inclined relative to the plane in which most planets orbit. These factors combine to yield an extremely low probability of any significant interaction with our planet. In practical terms, the chance of 3I Atlas approaching dangerously close is effectively zero for any foreseeable future. Nevertheless, astronomers monitor these probabilities carefully. Even objects with initially low impact probabilities can experience changes if their paths are altered by gravitational encounters or outgassing events. For example, if a comet passes near Jupiter, its trajectory can shift enough to modify future MOID calculations. Though this is not relevant for 3I Atlas, which is passing quickly and at a distance, the principle underscores why continuous observation is essential. Probability calculations also extend beyond Earth. Scientists estimate the likelihood of close approaches to other planets, moons, or the Sun itself. These estimates help mission planners decide whether a comet might be a candidate for spacecraft observations or whether its path could pose risks to satellites or future crewed missions. For interstellar comets, these calculations also provide insights into how often such objects might interact with planetary systems, offering clues about the dynamics of galactic material exchange. These probability models rely on a combination of analytical equations and numerical methods. Analytical equations give quick approximations and help identify key parameters like MOID, while numerical simulations provide detailed evolution over time, capturing complex interactions that cannot be solved by hand. Together, they allow astronomers to build a comprehensive picture of a comet's future. What makes this process remarkable is the scale involved. A comet like 3I Atlas is a relatively small object, yet its position can be predicted across millions of kilometers with extraordinary accuracy. This is possible because the laws of motion and gravitation are so precise, and because modern observational instruments can measure positions to astonishing levels of detail. Even slight variations are accounted for statistically, producing reliable probability estimates that guide our understanding of potential risks and opportunities. As a result, the mystery surrounding objects like 3I Atlas is balanced by clarity. We may not know every detail of its distant past or ultimate destination, but we can describe its future path through our solar system with remarkable confidence. This combination of curiosity and precision reflects the essence of astronomy. We watch the skies not just to wonder but to understand, to transform uncertainty into knowledge. As 3I Atlas continues its journey, the probabilities of future interactions will shrink into insignificance. It will become another faint traveler moving steadily into the dark, its path mapped, its influence calculated, its story added to the growing catalog of cosmic visitors. For now, it is a reminder that the universe is vast, interconnected, and governed by laws we can learn to read like the pages of an ancient celestial book.